Hey guys, today I'd like to show you how to do an analysis of a simple truss. We're going to be working in metric. We have a truss that is 16 meters long in 4-meter increments and 3 meters high, and these loads are applied to it. It has a pin connection on each end, and here's right here you can see that the structure is determinate. I just wrote that out for you. You can stop the video and check it out, but it is statically determinate. So we're going to go ahead and draw that up in Robot. Go to File, New Project, Truss 2D Design. So right now I'm in USCS, or pretty much like Imperial, and we're going to go to Job Preferences, Metric, yes, okay. So we're in metric now. We're going to go ahead and set up our grid. We want 4 repetitions at a distance of 4 meters. Click Add. We want Z, 1 repetition, 3 meters, Add. Changes to lettering, just for practical purposes. And we have our grid set up. So what I'm going to do now is go to Load Types, add just some random load because I don't want it, because this will include self-weight and I don't want to do that. And then you could leave this as anything, it doesn't really matter because we're doing a simple case, but I'll just name it dead load. Okay, so close. So next I'm gonna sorry, I have these from earlier. So we're gonna go ahead and click bars. So you want your bar type to be simple bar, and in here you're gonna click what type of section you want. So in order to create the section, you will be in standard by default. You click on parametric and go to tube. Right here it gives you the outside diameter and the thickness of the tube, but we want a solid tube, so we're just gonna say solid. And I'm gonna use an arbitrary dimension and say this is 10 centimeters, and we're gonna call this pipe 1. You never had to use a tube, you could have used another member since it's just a simple analysis. So I'm gonna go ahead and click add, and it's in there, it's pipe 1. Okay, so now I'm gonna draw my members. What does this look like? Okay, I made a mistake. Control Z, Control Z, click back in here, do that, do that, do that, do that, and I'm gonna come on this side and I'm gonna do the same thing. Okay, so now we have all of our bars drawn. We're gonna go ahead and define our supports. Now I want to point out that on here we have 2 pin supports inclined at 45 degrees. Now it doesn't really matter whether or not they're inclined at 45 degrees, 105 degrees, 369. Doesn't matter because they're both pinned. If this was a roller though, it wouldn't matter. So I'm going to show you guys how to make a angled support. So we're going to go here, click new support definition. We want all these, choose a direction. I'm going to say 45. I'm not going to get fancy and name this anything, so I'm just going to call it support 1. Then I'm going to do this again. You can see the locked positions right here. Then go negative 45. Okay, call this support 2. And you can see they're both added in my supports. So click support 1, do that. As you can see, there's a little box here that shows you where is connected. If I was supposed to put support 1 here, then you'd see the orientation of the box is not how I want it to be. So I'm going to do Control Z, click on support 2, and then do it. And then see the box is correct. So zoom out, close. So I'm going to go ahead and I already did my load types. I'm going to do load definition and say nodal force -12 and click add, and it was in kilonewtons. And then click back on nodal force -6 and then click add right there. Okay, so I can click close now. My loads disappeared. We can come down here, click load symbols, and they're there. How do I know if they're right? Click the button next to it, and it shows me the value of the load. So all my loading is correct. So we can continue and go on to the next thing. What else have I left out? Is there anything else? I don't think so. I think it's all drawn up now. So we'll go ahead and do the calculation and go to results, diagrams for bars, FX, apply. I can't see any values, but I want to see some values, so I'll come here, parameters, and say text, apply. So you can see that this has a 25 value of 25, value of 4, value of -3, value of 20. Over here, should also be a value of 25, but it doesn't show up. I'm not sure why. And you can change it to filled if you want to see that, or if that looks better to you, or fence. And you can also let it differentiate between tension and compression forces. So I'm doing that. One thing I want to point out to you guys, in robot, compression is positive and tension is negative. So compression is positive, tension negative. So this 25 right here is a tension. Did I say that right? No, this 25 is a compression. My bad. Yeah, 25 is a compression force. So yeah, and also the moments, if it bends concave up, then that is negative. This sign convention is different from what I'm accustomed to. I'm not sure what's the major thing. I know in the US most people like to have concave up mean positive moment. That would be the beam as a smiley face. And also they usually, or what I'm accustomed to, is having the tension be positive and compression negative. So just be careful with those signs, and whenever you're working on a project, so you know what's going on. You should be able to have an intuitive feel from any structural analysis that you know whether or not it's compressive or tensile. So we can go ahead and say, what were the reactions on the supports? As you can see in the x direction, it was for node 1 it was 24, FZ 15. So, and for node 7 it was -24 and 15, which makes sense. We can go ahead and close that. Let's say we can also bring those upper forces and stresses and have all those tables. Let's say I wanted to have a more detailed analysis of a bar. So let's say bar 9, for example. We're going to go ahead and go to results. So this is called the layout drop-down menu. So go to the layout drop-down menu and click on results, and then you get some more options. Detailed analysis. You want FX. So it says open a new window. Click apply, and now it shows you the bar. This doesn't seem too right though. It is right. It is. Yeah, so 25 is up there. So we can also find out the stress analysis of the bar. And here, this is viewing the member from the different axes, whether top or whatever. And this gives you the normal stresses on the bar. And it's just a simple diagram because it's just a truss member, so it could have only gotten tensile or compressive forces. You can change which member you want to view if you can click it in here and click selection, and it'll do the results again. So here it is. You can see that the values, the stress values are different. I'm going to go back and go to structure model. So one thing I want to remind you guys is that even though this has two pinned ends, it's two pinned ends. It is a statically determinate truss. So what I'm about to do now is to extend the analysis of this truss. So let me get rid of these diagrams. Click on that, apply. Okay, they're gone. Oh, one thing I forgot to point out, deflection. You can come down here, click the deflected shape. I know it's very exaggerated here. You can also go back into results and displacement. No, sorry. Diagrams for bars, deformation, click apply. And in here you can do a video, you can let it move, you can change the frames per second and do all that stuff. So y'all can play around with that, have some fun. But as I was saying, I'm gonna go ahead now and change. I'm gonna put on some initial load cases, such as a temperature increase or um, a initial displacement at a support. So these are added like forces. So I'm gonna go ahead and put a, let me see, 5-degree increase on member 12 right here in temperature. So we're gonna go to load definition, click on bar, click on thermal load. Let's say 5 degrees Celsius, add 12, and then we can, I'm not gonna say close because I'm gonna put another one. You can do an initial imperfection from the bar being manufactured at the wrong length. It can be positive or negative. You can do this as a relative or absolute scale. Let's just go ahead and do one. I'm gonna say, how long were these? Let's say 0.5 meters absolute, add. I'm gonna click on member 9 and then impose displacement of a support. So I'm gonna say, let's say Z went down by, I don't know, 2 meters is too much. 0.01 meters, which 1 centimeter. So click add, then just click right there. Whoops, I made that up. I made that, sorry. So down, went down. One thing to notice is that it follows the local axis of the support. So have to be careful with that if you have a rotated support. Then we can click close. And then we can run the analysis again. Go to results, diagrams for bars. And as you can see, the forces in the bars are the same exact thing. One thing to remember is that for statically determinate structures, any initial imperfections or thermal loads or anything like that will not cause an increase in forces in the bars. However, if we were to look at the deflection, it went crazy. It's all over the place. It's pretty much sideways where everyone's dead. Everyone is dead. Um, so Yeah, all the deflections changed, but the forces in the bars have not because the truss is determinate. If we were to impose another support condition, then this would not be the case. The truss would no longer be determinate. Let's go ahead and do that. Let's just put a roller right here. Let me unlock the model. Uh, Let me put pinned. Okay, and then close, and then run. Yeah, see now the forces have gotten extremely large. It is crazy. I'm not even sure what these numbers are. 23582. We could just go in here. Forces. Uh, so I see a bunch of forces here. I'm like, which one is the highest? Okay, you can just go down here to global extremes. Bam, our max is 70,000 kilonewtons, and our minimum is negative 42,000. So that's quite large. That is quite large, guys. Let's go back to the original and see what it was before I impose that additional support. Let me just take off this diagram real quick. Apply. It's making everything. I'm just pressing apply again just to refresh the screen. Okay, so just go to supports, delete, and then click right there. And then we'll go ahead and run this again and see what it is. Let's see what our forces are. Much lower. We're back to 25 kips as our highest and -3 as our minimum. So that's just how to do a simple analysis of a truss in robot structural analysis. If there's anything else you guys would like to find out about modeling this truss, I'll probably get to it in a couple of weeks. Soon I'll extend it to 3D and also for frame members. So if you like this video, like, comment, share, subscribe. Please let me know if you guys would like me to do something more or anything like that, or if you have any questions about the videos. I enjoy doing this for you guys, so please let me know. Have a good one.